Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome back in lecture 02 part 11. Student, in this lecture we will discuss how to calculate loads for a beam design. This is important lecture because it is you can say the initial part of a design example of beam designing or slab designing, any column member, any member. We need loads. So the proper and accurate calculation of load is very important while we are doing the structural analysis, right? The correct prediction is very important. So how to calculate loads for a beam design? First of all, we have to find out loads per square feet. We need loads per square feet or per square meter, that is designated as kilonewton per square meter or kip per square feet. This is important. So let me share you some density of various materials that will help you to remember the various densities of various material. Here you can see in this graph, or in this chart, sorry, in this table, you can see the weight of the plain concrete, right? This one, the top one, its density varies from 2300 kg per cubic meter, and in kilonewton it is 22.6 kilonewton per cubic meter, while in pounds it is 144, while in for an RCC, that is reinforced concrete, it is equal to 23.6 kilonewton per cubic meter, while it is taken as 150. Similarly, for clay masonry, this is 1900 to 1930. We all in previous lecture we used this. Similarly, we also use this for lintel load calculation 18.9. And for masonry, all type of masonry is taken 120 kilonewton pound per cubic feet. Similarly, for earth, in today's lecture we will consider this density, that is 1600 to 1800, 15.7 to this, and this is 100 to 110. It varies. So all these are the weights of various material, right? You can see here, and we will use these weights. If these weights, these materials are supported by our slab, are supported by our beam, so we need these unit weights of the material. So please remember this chart, it will help you. Similarly, here you can see the uniform distributed live loads according to ASCE07 code, because these are the code specified values that for a private apartment, school, classrooms, we will consider this loading as 40 pound per square feet or 200 to 1900 newton per square meter. Similarly, for offices and various buildings, I will share this as well in the ASCE07 when we are designing any beam or slab section. So these weights are important, and you must know these weights, and it will help us. This table is also important because sometime when we designing any beam or any slab, we will do example who are in SI units as well. So that why you must remember this table, because in if you see here the use designation, it starts from number, although number 2 is not used in use designation or in use units, so it starts from number 3 to number 18. So number 11, and there you can see stop number, there is no number 12, number 13, number 15, 16, 17 bars. While in SI units designation, you see here the corresponding designation, that number 3 will be designated as number 10, number 4 will be designated as 13. This is in millimeter, right? 13 millimeter, number 4 equals to 13 millimeter, number 5 equals to 16 millimeter, and most of the time we will use this 25 millimeter bar, that is equals to number 8 bar. So this kind of designation, their solid diameter and their nominal areas and their nominal mass, kgs per meter, we will use this in our calculation. So this is important to understand, and we will use this in design, right? So how to calculate loads? This is an important question. Let's say for a slab, because we calculate loads from slab and then we transfer the slab loading to the beam by using the equivalent the tributary area, as we discussed in part 08, right? Either considering the trapezoidal loading or triangular loading, and then converting that triangular loading to equivalent UDL loading. So I have already recorded lecture 02 part 8, so please go there and watch that lecture. Let's say we do calculation for top roof, because the top roof weighting is sometimes different from the intermediate floors. So for example, let's say if I have draw a structure right here, let's say this is my structure, and here these are the various floors. So this is my top floor, top roof, right? This is roof. So on roof there are different types of loading, like you can say snow loading. So snow loading is not present over the intermediate floors, so that's why snow the top, and here you can also see asphalt covering. There we will also use sometime earth filling, so that loading is absent over the intermediate floors. So that's why the roof loading is different from the intermediate. Let's say we are using 125 mm thick slab. Although in ACI code 318 the minimum thickness, which is denoted by H, of the slab is 6 inches, that is 150 millimeter. So let's say we have 125 mm thick slab, so and we have earth filling over it, we have brick tiles over it, and how we can calculate the loading over such member. Yes, let's say we have 125 mm thick slab. This is slab, this is for slab. We have 100 millimeter, this is almost 2.5 to 3 inch earth filling. This is for insulation purposes, to control the heat. And similarly brick tiles on the roof, we also use these brick tiles, right? This is almost taken as 38 millimeter or 1.5 to 2 inches thickness. Now to calculate the loads of these materials, first of all 125 millimeter thick slab, the weight is simple. We just take the thickness of the slab. Now this is RCC, so the density of the RCC is 2400 kg per cubic meter. This is 150 pound per cubic feet, and divided it by 1000 because this is in millimeter. The final value will be 300 kgs per square meter. This will be in square meter because this is in meter, right? And this is kg per cubic meter. So 1 meter cancel out with 1 meter, so that's why this is in square meter. Similarly, earth filling, that is 100 divided by 1000 times the density of the earth filling. The density of the earth filling in FES system, it is 100 to 110 pound per cubic feet, while in SI units it is 1800 kgs per cubic meter. This is an MK system, right? So it will be 180 kg per square meter. Similarly, brick tiles, we have brick tiles over it. This is 38 mm divided by 1000 multiply with 1930. This is the density of the brick tiles, round about 110 to 120, right? So this comes out to be 74 kgs per cubic meter per square meter. And the total load, we will use this these loadings in our design example. So the total loading will be how much? This is, if we add these values, this it comes out to be 554 kg per cubic square meter. Sorry. Now let's say we are assuming live load. Let's say we are assuming this is an apartment or a school building. So for school building, we know in the previous table we will discuss this it will be taken as 200 kg per cubic meter. So that's why the factored loading, now the factored loading, which is denoted by WU, equals to 1.2 dead load plus 1.6 live load. If we have snow load, earthquake load, wind load, so we will use different load combinations, but this time we have only dead load and live load, so that's why this one will be the governing combination. We just plug the value of dead load, that is 554 plus 1.6 times load 200 to convert into kilonewton. So 9.81 divided by 1000 kilonewton, right? This is kilonewton. So finally what we got this from this, it comes out to be 9.66 kilonewton per square meter, and this is the final loading for the roof. This is important. After getting this load, let's say we have an interior beam, and interior beam, as we did this calculation in part 08, and we have double trapezoidal area. So in that case we will find out the equivalent width as we derive the equation for that width. So we will find out that equivalent width, and that equivalent width will be multiplied with this width. From once we multiplied, because that width, let's say that is equivalent width, will be multiplied with this 9.66 kilonewton per square meter, and that width will be also in meter. So that meter goes with this meter, and that why we will gain x kilonewton per meter. So this load for the design of the beam, it will be converted into an equivalent UDL loading by just multiply this area load with the equivalent width. I will explain this in design example, but you must remember this calculation at this time. The next one is, let's say for intermediate. For an intermediate case, let's say we have intermediate floor. So for an intermediate floor, let's say we have a slab thickness is 150. So RCC slab is 150 millimeter, right? And we have 75 mm, because we don't have, this time we don't have earth filling, right? So that why we have 75 mm brick blast. We have 40 mm thick PCC, right? We have 40 mm thick PCC, plain cement concrete, which is used as an undercourse for tiles. And we have 20 mm thick terrazzo finishing. We have terrazzo finishing, and then we have occupancy type office building. We have type of structure is occupancy type office building. So we'll go to that chart and we will find the live load for this type of occupancy type office. Right, from there we will find out the live load, and the live load, if we search in that table for office building, it comes out to be 250 kg per square meter, right? Per square meter. Now how to do that calculation? Now this is important, right? This is important. So for an intermediate slab, first of all we have 150 mm RCC slab weight, that is 150 divided by 150, sorry, this is not 100, this is 1000, times and the density, that is 2400. So from this we got 360 kg per square meter. 2, we have brick ballast. So brick ballast, the thickness is 75 divided by 1000 times the density of the brick ballast. It is also given in those tables, it is 135 kg per square meter. Third, we have PCC plus terrazzo, because when we are providing terrazzo finishing, we have to provide first of all PCC, that is round about 1.5 to 1 inch thick. So that way, combining the thicknesses of both layer, that is 60 divided by 1000 multiplied by the densities, that is 2300, this is a PCC density, and it comes out to be 138 kg per square meter. We had total loading, total dead load will be, all these loadings will be 633 kg per square meter, and we have live load, that is from table, it is 250 kg per square meter. So the final factor load is 1.2 dead load plus 1.6 live load, and if we plug all the values, we got 11.38 kilonewton per square meter. We will multiply this area load with the width of the equivalent triangular loading or the trapezoidal loading, and we will find the load kilonewton per meter or kip per feet. So we will use the equivalent width, and I have already recorded a lecture over that is part, I think so, that is part 08, right? Part 08, and here I have already derived those equations. In the case of a one-way slab system, the width, the equivalent width will be Lx by 2 plus cantilever portion, and similarly here in this case, this is not the case, this one we will use this case. This is, here is my double trapezoidal load. So in that case we can see we have 4 cases, while for the beam this is B1, so the short beam this is B1, so we have double triangular loading. In that case the width is equal to the equivalent width, the equivalent slab width for calculation of bending moment for B1, it is equals to 2/3 Lx times Wu, which is the unit load which we have calculated right now, right? So this is the width, right? This is the width. We have to multiply that load which we calculate in this lecture, and we will multiply that load with this width. We will got the load as kilonewton per meter or kip per feet, but this is for this beam, this B1 beam. Similarly for B2 beam, which is the short exterior beam, in that case the equivalent slab width will be equals to the 1/3 of the Lx plus cantilever portion. So we will multiply this with that. Similarly in case of a B3 beam, that is my B3 interior longer beam, in that case the equivalent width is this one, right? This one, and I have already find out the width will be, the final value will be Lx times 1 minus r divided by 2 into f. Similarly for the B4 beam, which is this one, which is the shorter longer beam, right? Shorter long exterior beam, this one, right? This one. For this one, the equivalent width will be this one, Lx into 1 minus r squared divided by 3 divided by 2 plus c into portion. So this will be multiplied with those loadings h as we already derived right here, right, with this loading. So that equivalent width will be multiplied with this area loading, and we will got the load as kilonewton per meter per feet for the design of beam. Thank you for watching. See you in next lecture.